Welcome back to the lecture Biological Wastewater Treatment. Today we will learn something about special types of biological transformations with a focus on microorganisms that are useful for biological wastewater treatment. Yes, and we make a classification of microorganism a little bit different than you may know. Also today there are modern techniques like PCR available, but we are looking mainly on this classical scheme with a focus. Also first of all microorganisms in wastewater treatment systems has to grow. We want to have a high biomass concentration, and first we are distinguishing between the carbon source. Microorganisms that need or that are used hydrocarbons, organic components, for their anabolism, their cell formation. These are called heterotrophics. On the other hand, we have also many microorganisms that need carbon dioxide for the formation of biomass, of cell mass. These we are calling autotrophic microorganisms. Yes. Beside this scheme, the anabolism, also the biomass production, they need to do so energy source. And therefore we are distinguishing between different types of energy sources. Also one option is that they are using chemical energy, and so we call these organisms chemoheterotrophic. And we are also making the distinction in this case whether they are using organic components for the energy supply, also for the catabolism, then we call this chemo-organoheterotroph, or if they are using inorganic components, then we are calling this chemo-lithoheterotrophic organisms. Yeah. The other source that they may use is the radiation energy, also sunlight, for example. In this case, we are calling this photoheterotrophic organisms, but you see this energy utilization of radiant energy you mainly see with plants or algae or something. Therefore, there are only few organisms are able to make this metabolism. Yes, for the autotrophic microorganism, also they are using CO2 for their cell formation, and they can also use chemical energy, also using organic components, then we are calling this chemo-organo-autotrophic, or they are using inorganic components for the energy supply, then we are calling this chemo-lithoautotrophic microorganism. Also we will have examples later on, for example some nitrificants. And we have all this photoautotrophic microorganism. This is the world of all plants and nearly all algae, but some cyanobacteria, they are also in this field. Also finally they only need sunlight and CO2, and then they feel happy, maybe some nutrients. Yes. If we have a look to the elementary composition of biomass, then we will find that mainly the half of the biomass consists of carbon. We had in the lecture before as well this formula for biomass, this hypothetical mass sum formula, which is respect on this scheme. Then of course we have hydrogen 7%, oxygen 32, nitrogen 11, and P 1 point, maybe a little bit more, 1.5%. There are some other elements inside as well, like sulfur and other metals, but this we want to negate. Therefore we see that they are needing these nutrients, and they maybe need hydrocarbons, or at least they need carbon. Yeah, first we want to have a look to the chemo-organoheterotrophic metabolism. That means for the energetic metabolism, also the catabolism, they are transforming hydrocarbons to products like CO2 and water and gaining chemical energy out of this. And this energy is stored in a special form in the cell, is used for the biosynthesis, where they are using hydrocarbons and transfer this to biomass. Of course, they are using nutrients as well. Finally, the anabolism is used, in this case, glucoses as an example, organic molecule. This is widely used because many microorganisms are able to make use of it. And finally, we need some nitrogen, and they are making biomass and water. Yes, and how they gain the energy, and this is differently. First, we have a look to the aerobic endogenic metabolism. Now, if they have dissolved oxygen, dissolved pure oxygen inside the water, then they are able to make a biological oxidization of glucoses to CO2 and water, and they are gaining nearly 3000 kilojoules per mole of energy for making this oxidization. Of course, this is enzyme catalyzed, and they're getting out a lot of energy. This is called the aerobic metabolism. But the microorganism can do a lot more. If they don't have dissolved oxygen, then they can switch to the anoxic energetic metabolism. This means that they are using other formed chemical bound oxygen. For example, nitrate or nitrate. Yes, and they can work together with reduction equivalents. In the microbiology, this is mainly expressed in this form because this is a part of an reduced enzyme, and they are transferring this to elementary nitrogen. In the ideal case, we will see maybe there can happen something else, water, and to make the balance clear, HO minus ions. And they are gaining chemical energy, in this case mainly the same amount as here, a little bit less. And also they can make this for nitrate. Of course, they are producing less water in this case. We can also make the comparison with oxygen. If we have dissolved oxygen, this reacts in this form with this reduction equivalents and forming, of course, water. And this is quite important, as we will see. If we have 8 grams oxygen per 1 mole of this reduction equivalent. If we go back, we see we have here 4 reaction elements for 1 O2, and this O2 has 33 grams divided by 4 is 8. 8 grams O2 represents 1 mole reduction equivalent. And now we have, in this case, 5 reduction equivalents that is required for 1 mole nitrate. And finally, this oxygen represents COD. This would be the amount of organic material which we are measuring with some parameter COD. This represents 8 grams COD per mole, and this we are dividing by 14 gram nitrate N per mole. And this is gaining in 2.83 grams COD that is required for the reduction of 1 gram nitrate N. In reality, this is a little bit more because the microorganisms are also growing and not only making catabolism. They are using COD as well for the growth. This is the minimum that we need. Therefore, we need some COD for the denitrification. This is reduced if we are using nitrate. In this case, we only have 3 times 8, and this is resulting in 1.7 grams COD per gram nitrate N. Yeah, but finally these anoxic metabolism can use like acetic acid or glucoses, and this is leading finally to CO2, water, OH minus, and energy. Finally, to find the stoichiometric coefficients, in this case you can make the elementary balances and as well the charge balances. If we don't have nitrate, nitrate and dissolved oxygen, the microorganisms are very flexible. They are looking what else is in the water, what else could be reduced. And one component which is in the water is the nice sulfate. Sulfate is widely used in the water, especially in industrial wastewater, because sulfuric acid is the cheapest acid available, and therefore it is very difficult to skip. And what they are doing, they are making CO2 and water, but they are producing as well sulfides and chemical energy. But this is lower, a lot lower than from the anoxic. Or they are making pure sulfur, which is better as a storage product. If there is maybe an excess of glucoses, this can be also the case. But finally, the microorganisms that are storing elementary sulfur are normally very hydrophobic. It means that air can attach very nice on these particles, and they are floated and forming easily bulking sludge. Therefore, this is also not really wanted. But if they don't have any bound organic carbon, then they are switching to the anaerobic metabolism. Also we are distinguishing between aerobic, anoxic and anaerobic. Anaerobic means there is only oxygen in form of water and CO2 available, and in the organic components itself. What they can do, for example, they can produce from ethanol acetic acid, or they can produce also from propionic acid acetic acid. These are very important steps in the anaerobic sludge treatment in wastewater treatment plants. But finally, there are other important things in the food industry. For example, from sugars, they are making lactic acid or ethanol, which is a fermentation product, and this is used for thousands of years. For the conservation, this is here sauerkraut, yogurt and things like this. And alcohol, you may know, as form of beer or something like this, which the people like to drink. Okay, now let's shift to the chemolitho-heterotrophic metabolism. This sounds a little bit strange. They are using inorganic components for producing energy. Also they are using, for example, hydrogen or something like this. And with this chemical energy, they are using organic components to form the biomass. And this is really seldom in the wastewater treatment, but some methane bacteria are making this way. The catabolism, so the energetical production, is from hydrogen. Hydrogen is produced, as we remember before, from fermentation products, and CO2 is put together to methane. And this is gaining as well energy. But maybe you have to invest energy. We will discuss this later. But this is very important in biogas production. This is one main pathway for the methane formation. Yeah, photoheterotrophic metabolism means the microorganism receiving energy due to radiation, normally sunlight, and they are using hydrocarbons to form biomass. This is also very seldom. Some sulfur-free purple bacteria or some sulfur bacteria are making this, that they are using glucoses and radiation energy and producing CO2 and hydrogen. This is maybe useful in the biological hydrogen production. This was tested already. This would be a very smart situation, that you can use wastewater and sunlight and produce hydrogen, the potential energy source of the future. But finally, this is not really productive until now. But you never know, this is at least possible. Now we are coming to the chemo-organo-autotrophic metabolism. This means that they are using hydrocarbons and producing a CO2, but they are using carbon dioxide for the biomass production. This sounds also a little bit strange, but there is also one important reaction required, but finally the metabolism of the autotrophics, the anabolism, also the formation of biomass, goes from this scheme. They are using CO2 and nitrogen and of course phosphate and so on to produce biomass. And in this case they are producing as well oxygen. Also plants are doing so, therefore if there is sun, they are making photosynthesis, they are producing cell mass and releasing oxygen. Yes. But finally, this type for the energetic metabolism for the chemo-organo-autotrophics, these are some methane bacteria. They are using also acetic acid for the production of methane and CO2, and therefore they are gaining some energy, also not really much, but a little bit. But the interesting thing is, if they don't have carbon dioxide, also finally they are producing this by themselves. But if you're adding barium, for example, and removing all carbon dioxide, they don't grow. Also they are growing on carbon dioxide. Interesting thing. Now we're coming to the most important pathway in biological wastewater treatment, the chemolyto-autotrophic metabolism. We will see later on why. Finally, they are using inorganic components for the energy production. Also products are nitrate, nitrate and sulfate, also they are oxidizing. Then in this case ammonia or sulfite or something like this, gaining chemical energy, and they are using carbon dioxide for the anabolism, for the biosynthesis. Also one important fact is the nitrification. There are ammonia oxidizing bacteria. They are different. Also one example is Nitrosomonas, but there are a lot of other microorganisms as well that are doing this, and they are for the catabolism, also the energy metabolism, they are oxidizing ammonia to nitrate and HO3+ to make the charge balance equal. Also finally here is your 2+, and it's resulting in 2-. This is not going, and therefore the trick is to implement H3O+ or OH- to make the charge balance complete. The anabolism and catabolism as one is that you are using 55 ammonia and lots of water and bicarbonates, which is leading to biomass, and 45 nitrates. Also this means the main part of the ammonia, nearly all, is used for the catabolism. Only this 2% or something for the anabolism. We have as well this nitrate oxidizing bacteria, one parameter is, also one example is nitrobacter that are oxidizing nitrate. They are forming from nitrate to nitrate. And there we see also the anabolism and catabolism together. Normally microorganisms are preferring ammonia as a N source, but they are able to accept others as well. But this leads as well to using 400 nitrate moles to only one N is used. Very, very few N are used for the anabolism. The main part, over 99%, is used for the catabolism. Altogether, normally, this is in this case 45 or 55 moles ammonia is used for the catabolism only. Therefore, we are normally considering only the catabolism. And if we are making the nitrification complete, normally in the wastewater we are not really interested in details in this case. If we look, we want to change, bring the ammonia to nitrate, and there we need 2 mole oxygen and producing 2 mole H3O plus as well. This is, we call this nitrification process. This is one important step for the nitrogen removal. And due to the fact this is done by autotrophic microorganisms, they are growing slower than heterotrophic. This is the limited step in biological wastewater treatment. Therefore, this nitrification is quite important for the design of wastewater treatment. And later on, of course, the denitrification, we have to get rid of the nitrate as well. And on the COD, we don't have to worry if this is working. This we will see later in the lecture. But 2 moles oxygen per 1 mole ammonium N means that we need 2 times 33 grams oxygen per 14 grams ammonia N, and this means we need 4.57 grams oxygen per 1 gram ammonia N. In wastewater, municipal wastewater, due to the water saving, we have up to 80 grams ammonia N per cubic meter. And then you can imagine how much oxygen we need. The main part of the oxygen entrance in the wastewater treatment plant is due to the nitrification. And this is also the reason why ammonia has to be removed. It will result if there's only 2 grams ammonia N in the effluent of a wastewater treatment plant. Finally, this would be consuming all the soft oxygen if the temperature is higher than 10 degrees centigrade. Normally we have oxygen is very poor soluble in water. Therefore, we have normally less than 10 grams per cubic meter the soft oxygen in the saturation case. The other fact is the alkalinity. 2 moles of He3 plus per mole ammonia N are consumed. This means 1/7 mole H3O plus per 1 gram ammonia N. And finally, if there would not be a buffer system inside, the pH will be dropped down. But we have normally the bicarbonate concentration, which is the main chemical for the buffer capacity, and the concentration of this bicarbonate, in this case, we are calling alkalinity. We have heard this in the lecture before as well. And finally, this is reacting with 2CO2, which is stripped out. And if the alkalinity is, we have to have a look, the alkalinity has to be high enough to receive this H3O plus ions from the nitrification. We have other interesting microorganisms inside this group, the chemolithoautotrophic metabolism. The Thiobacillus thiooxidans is an oxidizer of sulfite, or H H2S. Finally, the oxidation product is sulfuric acid or an acid, which is quite aggressive. And this is a problem, for example, in sewerage systems. Normally the water flows there very slowly, long. We have desulfurication, the formation of H2S, but in the headspace of the sewer there is oxygen, or in the biofilm in the sewerage systems there is oxygen, and they are living this Thiobacillus thiooxidans and produces sulfuric acid. And sulfuric acid and concrete reacts, and this is, for example, destroying the infrastructure. Normally a sewerage system is designed for 90 or 100 years, but in the 70s they are using a lot of concrete piping, and this was already destroyed after 30 years due to this organism. We have also Thiobacillus ferrooxidans, which is used in wastewater treatment as well. Normally we have to add iron salts, iron or aluminium salts, for the precipitation of phosphate. And the cheapest form to buy iron salts is this iron sulfate, also iron 2 sulfate. This is called green salt. This is a byproduct of the titanium dioxide production, and therefore quite cheap available. And normally if we are adding oxygen, we can oxidize this to iron 3 sulfate. And iron 3 sulfate reacts with phosphate, for example, to produce iron phosphate for the precipitation. And therefore many, at least bigger wastewater treatment plants are buying this green salt quite cheap, even though it's quite complicated to bring it in solution, but to save money, and oxygen consumption is in this case quite low, but there are bacteria, they are adapted to make the oxidization, and they are having the precipitation. Now we are coming to the last metabolism, the photoautotrophic organism. Also the sunlight produces the chemical energy inside the biomass, and carbon dioxide is used to produce biomass and oxygen. Also this would be the biosynthesis for autotrophics. This is all plants, nearly all algae, cyanobacteria, they are called blue-green algae, are making these organisms. This is also important in lake systems. Also one aspect is that they are bringing oxygen in the water, and this can be used by bacteria that are degrading components in the wastewater. On the other hand, also this behavior is changing the pH, and if you see, this is an acid. Okay, this is a base, but finally the pH will go up in lakes like this, and maybe it's also good for some type of hygienization. Also in lake systems, this is a useful trick, also low-tech systems or something like this. These are the metabolisms. We will briefly talk also about some other interesting bacteria, the so-called BWT bacteria. Also we can also bring the bacteria to the way that they are storing more phosphate than required, so then we can save precipitation chemicals. We will have later on a lecture especially on biological pee removal as well. But the idea in this is to make an anaerobic and an aerobic stage in series and bring the sludge backwards, recycle the sludge. And in these cases you can accumulate this BWT bacteria that have the possibility that they can store easily biodegradable components as polyhydroxybutyrate or other organic storage products. And the energy that they need for this process is delivered by polyphosphates inside the cells that is hydrolyzed to phosphate. That means in this anaerobic stage, the phosphate concentration is a lot higher than in the influent. Yeah? But now in the aerobic stage, these microorganisms can degrade this easily biodegradable components and gaining energy, and maybe some other hardly biodegradable components as well. But the microorganisms that don't have the storage product, they have less food and can't grow as fast. But in addition, they are taking in a lot of phosphate, more than for the cell growth. They are also producing polyphosphate storage products inside the cell. Yeah? And finally, somewhere you are removing excess sludge and the normal sludge and the dry matter. You have, as a biomass, you have 1.5% P, and in this case you have 4.5% P. And in this case you are removing more P than is only due to assimilation. And this process is called the O process, as a biological phosphorus removal. Yeah, another thing is in the anaerobic metabolism. We will talk about this later. I will skip this here. We will talk about this as well. But finally, there are going different types of processes. The hydrolysis with fermentative bacteria, the acetogenesis, also with fermentative microorganism, but the acetogenesis, they are producing acetic acids and hydrogen. These are the only two components that are used for methane bacteria that are producing methane and carbon dioxide. Beforehand there is also ammonia and sulfite separated from the, for example, amino acids. But we will talk about this as well later on. Now you had a brief overview about this metabolitic pathways which are useful for biological wastewater treatment. In the next lecture we will talk about how fast they can be degraded, about kinetics. Thank you very much for your attention.